Hi, today I have this interesting thing. So this is a Compass computer, GM9. On the front there is a circular connector. There is also here a small compass card which indicates the heading. Here there are two adjustments. Okay, so normally this instrument permits to synchronize a directional gyro, something like this one, for example. The synchronization is performed using a magnetic compass like this one. Okay, so we have on the rear of this device different electronic boards, okay, which correspond to this sticker here. So this board is a gain control module, the slaving module, and an amplifier module. So this seems to be the power supply. Okay, so this board is effectively the amplifier module. Okay, so we have two transistors in TO66 to N3054, classic transistors. This is a servo amplifier. So the complete module here is a servo amplifier. And this is the slaving module. So there are several ICs with the same part number, MC1539G. They are probably op-amps. This thing is a transformer. It is something classic in vintage avionics. There is one relay also. Now this is a gain control module. And there is another module here on the bottom side. Now there are several logic ICs, 54 series, and several transistors. We can see we have 4 identical circuits here. Okay, so we have some flip-flops here. Okay, so this is a GK flip-flop. There is another one. And this is a counter, 4 bits counter. I don't know the purpose of that board. It looks like a stepper motor control, but it is very strange. And here we have several synchro transmitters. And there is also an AC motor here. On the bottom side we have the wiring of that thing. Okay, so we have a better view on the electromechanical stuff here. So this is interesting. So we can see that there is effectively a stepper motor here. Look at that. So this stepper motor is obviously controlled by the stepper motor driver board, which is this one here. We can see also that two wires are labeled U and D, up and down. It is difficult to see, but there is a differential gear. Okay, we can see it here. The differential gear permits to have an addition or a subtraction between two different shafts. There are 3 gears. So the rotation of the spider gear is the sum of the rotation of the 2 end gears. So this permits to have a sum. I suspect that the stepper motor permits to add or to subtract a given amount of angle. Okay, so this is the servo control. There are 4 synchro transmitters which should be connected to the rear connector. The motor for the servo control is this one. This is an AC motor. So the rotation of the AC motor is reduced using several reduction gears. So the stepper motor permits to modify the rotation of the final gear. You can have a better view on the differential gear. I did the complete reverse engineering of that device. I drew the electromechanical block diagram you can see on the screen. The functioning is not very complicated. The purpose of that device is to compensate the drift of the gyro. The directional gyro is shown on the bottom left on that page here. There are different methods to correct the drift of the gyro. One common method is to use a torque motor on that axis here. So when the torque is provided on that axis, there will be a rotation of the gyro on that axis because of the precession of the gyro. So this permits to have a correction of the drift on the gyro itself using a flux detector. The same we can see here. On that system it is different. The drift of the gyro is not corrected on the gyro itself, but it is corrected by that system. First, there is a servo control here, which is connected to a control transformer, which is connected to the synchro transmitter of the gyro. This permits to this shaft to have the same angle than the heading of the gyro. So that means that there is the same drift on that shaft than the gyro itself. The servo amplifier here is this one on that board. The goal of that system is to synchronize the output shaft, which is here, to the flux detector, which is represented on the left here. The flux detector permits only a long-term correction when the aircraft flies in a straight line. The flux detector has some limitation because of the construction itself. So this is an example of flux detector. We can see that there is a limited range of pitch and roll. And also there is a damping oil which limits the response time of that thing. That means that it is not possible to use a flux detector when there is a large change of attitude of the aircraft. So we can see that the shaft, which is an image of the heading of the gyro here, is fed to one input of the differential gear, which is here. So in the middle, this is the spider gear, which is the sum of the two end gears here. So we can see on the left, this is the correction of the heading, and this is the output shaft, which is corrected. Okay, the output shaft is linked to 4 synchro transmitters, and also to this internal small compass card here, which permits to visualize the result of that thing. The correction is performed using a stepper motor. So for that purpose, the flux detector here is connected to a control transformer. The frequency of the signals of the flux detector is 800 Hz. The rotor of the control transformer is fed to a synchronous detector, so this permits to have a DC voltage at the output. The voltage at the output depends on the difference between the angle of the Earth's magnetic field and the angle of this shaft here. So the goal is to have the same angle, so the error is translated into a series of pulses which drive the stepper motor in order to have a correction. The correction permits to modify the output shaft here until the error voltage is 0. So the correction is very slow. There is a special mode which permits to accelerate the correction, because the correction should not be too fast, because when there is a quick change of the attitude of the aircraft, the flux detector must not change the result on the output. So this loop should be very slow. The last thing is the calibration module. So the calibration module permits actually to add small DC currents on the coils of the flow gate sensors in order to compensate the static magnetic fields which are present around the flux detector in the aircraft. Also the control transformer which is connected to the flux detector can be adjusted using this helicoidal screw. So this permits to align the result to the flux detector. The first schematic is a schematic of the slaving module. This board here. The goal of this module is to convert the AC signal, which is the output of the control transformer. Actually, this is the transsolver. We will see later why this is a transsolver and not a control transformer. Actually, it is more or less the same, except that there is another coil on the rotor. We will see later the use of the second coil. So this is an error signal. This error signal is filtered. So this is a bandpass filter centered normally to 800 Hz. The signal is fed to this transformer, so this permits to have on the secondaries two voltages out of phase. So there is a synchronous detection using these two JFETs. The JFETs are used as switches. Each JFET is alternatively open and closed at a frequency of 800 Hz. On these two lines, there are two square signals, 50% duty cycle at 800 Hz. The output voltage is filtered using this filter. You can see that there are two different time constants. So there is a relay which permits to select this large capacitor. There is another amplifier which delivers a voltage which is connected actually to the rear connector. So this is the drive of the relay. This pin is connected to the connector. So when there is a low level, this permits to turn on this transistor and the relay is activated. So when nothing is connected, this relay is not energized. In that case, you can see that the large capacitor is used. So this is a strong filter. Otherwise, this capacitor is not connected and the filter is minimum. So there is actually a fast mode and a normal mode. So when nothing is connected, this is a normal mode, but a high-speed mode can be selected by connecting this input to the ground. So one interesting thing on the schematic is the generation of the two signals out of phase at 800 Hz. So I think it can be interesting to see the details of the functioning of that system. This circuit permits actually to generate two output signals, square wave, at 800 Hz with a duty cycle which is exactly 50%. So for that purpose it uses this transformer. The primary of this transformer is connected to the excitation of the magnetic compass. So this capacitor and this trimmer permit to adjust the phase of the outputs relative to the input sine signal, which is the reference of the compass. So this circuit is very interesting. If you want, you can pause this video and try to understand by yourself. So I will explain you how this thing works. So first you can see that there is a capacitor. So this capacitor is very important. So we can notice also that there are two current sources. So one is actually a current source with a current I0, and the second is a sine current, as you can see. So the sine current is 2 times this value. So I called this current 2I0. So there is a diode, you can see. So obviously this diode is used as a switch. The state of this diode depends on the voltage on the emitter of this transistor. So when the voltage here is above this voltage, we can call this voltage VC, for example. In that case, this diode is off. And when the voltage is below VC, this diode is on. I will write in red the different currents when the diode is off. So when the diode is off, that means that the voltage here is above VC. Okay, so this diode is off. So the current which flows through the emitter here is 2I0. So there is a current 2I0 here. So in that case, there is also a current I0 which flows through the capacitor here. Okay, so there will be a small increase of that voltage here. Okay, so now when the voltage is below V0, so when the voltage is below V0, this current is 0. Okay, so this diode is on. Okay, so the current 2I0 flows through this diode here. Okay, so now what we will do is to calculate the mean current in one period. Okay, so we can see that there will be a rectangular current. We can call the duty cycle alpha. Okay, so the mean current which flows here will be 2I0 alpha. The mean current here is 2I0, and the mean current which flows through the emitter equals the mean current which flows through the emitter of this one plus the mean current of the diode. Okay, but the mean current which flows through the diode is I0 because the mean current which flows through the capacitor is 0. Okay, so we have 2I0 plus I0 here equals 2I0. Okay, so we can say that 2 alpha plus 1 equals 2. So alpha equals 0.5. So this circuit permits to generate a square wave at exactly 50% duty cycle, whatever the secondary voltage is. So it can work with 10 volts or 20 volts. You will have always 50% duty cycle on the current which flows through this resistor. So this is a very nice circuit. The second circuit is the amplifier module. This is this board here. On that board there are two different things. The first, the main thing, is the servo control. So this is the control transformer which is connected to the synchro transmitter of the directional gyro. So this is the amplifier module. This is this module. So this is probably a standard part from the manufacturer, and they use this amplifier on different systems. So we can see, for example, at the input there are several resistors. So this permits to set the gain of the servo control. Okay, on that board they are connected in parallel, so the gain is maximum, but depending on the system and the different mechanical parameters, you can select a particular input in order to have a particular gain. This is why this thing is a standard board. So there is nothing special. The input is here, and at the output there is an AC coupling using this capacitor, and the output is connected to the motor of the servo control. And there is another circuit which is in the top of that page. So I don't know exactly the purpose of that circuit, but the output of that circuit is a relay. This relay actually permits to generate a short circuit at the output of the control transformer. So this circuit permits to inhibit the magnetic compass actually. So there is a transformer here, so the input is galvanically isolated from that circuit. So I guess, but it is just a supposition, that the input here is connected to the vertical gyro, probably the pitch or the roll maybe, in order to inhibit the magnetic compass when the pitch or the roll is too high, but I am not sure. But anyway, we can see that there is a threshold which is defined by this trimmer, and after that the value is rectified, and this permits to activate a relay. The relay is activated when there is a voltage above a given limit at the input here. The next schematic concerns this board. So this is the gain control module. So this is the main important circuit of that system. It is also maybe the most complicated. So the error signal is converted into a series of pulses which drives the stepper motor. So the stepper motor controller is here. So there is a clock for up counting and another clock for down counting. This is the main circuit for the conversion of the error signal. So this is performed using an integrator. So this point is connected to the output of the phase detector. This is this signal here. So the functioning depends actually on the state of these two transistors. So there are two identical circuits because one half is used when the error voltage is positive. In that case, we need to drive the stepper motor in one direction, and when the voltage is negative, so we need to rotate the motor in the other direction. So another circuit is used, but as you can see, they are identical. It is perfectly symmetrical. So at the output, there is actually a sawtooth like this. So either a positive sawtooth, otherwise it is negative. The minimum value is not constant. I will explain you in one moment why there is a variable minimum value here. So we can see that the output of the integrator is fed to two comparators here. Okay, and the output of the comparators is connected to two monostable, and the output of each monostable is connected to these two transistors, so one here and the second one here. So there is a negative pulse when the threshold is achieved here. So when the voltage at the output of the integrator is above 6 volts or below minus 6 volts, there is a pulse which is applied to the base of this transistor. So let's see only one circuit. For example, this one here, this is the up counting, the second one is for the down counting. Okay, so there is a negative pulse here. So this negative pulse permits to saturate this transistor here. Okay, so we can see that this transistor permits to connect this resistor here to the ground or not. So we can see that this transistor actually is a common collector transistor. Okay, so the emitter is connected to minus 15 volts. So we can see that when this resistor is left open, it is a state during the integrating time. So in that case, no current can flow through this diode and this resistor. So that means that this transistor is open In that case, the integrator works normally. When the voltage of 6 volts is achieved, this transistor turns on. This resistor is connected to ground. In that case, on the emitter, there is a given voltage, which depends on the base voltage here. And this voltage permits actually to limit the output voltage. So there is a fast drop of the output voltage of the integrator. And this voltage is identical to the voltage which is present on the emitter here, because you have actually two voltage drops, and there are also two voltage drops here. So the output voltage on that case is identical to the emitter voltage here. Okay, so the voltage drops to this voltage. It depends on the voltage applied to the base here. So this voltage permits to change the output frequency of the signal, because actually, if the minimum voltage is close to 6 volts, the frequency will increase because it will require less time to go to 6 volts. But if the voltage is low, in that case, the higher charge time is required in order to change the state. So this permits to modulate actually the output frequency and to change the gain of that system. Okay, so now let's see what is connected to the base of this transistor. So the base of this transistor is connected to this voltage doubler. You can see in details. And the input of this voltage doubler is that signal. Actually, this point is connected to the control transformer of the magnetic compass. Actually, it is not the control transformer, but a transsolver. So this is the second coil of the rotor. So there is a signal at 800 Hz here. So what is a transsolver? A transsolver is something between a classic synchro transformer and a resolver. There are three windings on the stator, like a classic synchro, but there are two windings on the rotor. So the two signals are actually proportional to the sine and the cosine of the angle of the transsolver. One winding is connected to the error amplifier. So when this thing is stabilized, there is no signal. That means that on the second winding, this one, there is a maximum signal. Actually, the amplitude of that signal is proportional to the horizontal component of the magnetic field, because the flaget sensors which are inside the magnetic compass is only sensitive to a magnetic field which is parallel to the flaget sensor. So actually this system permits to increase the sensitivity when the aircraft flies at high latitudes, for example above 60 or 70 degrees of latitude. The Earth's magnetic field is more vertical, so that means that the horizontal component of the magnetic field is very low. So in order to have more or less a constant rate of correction, there is an increase of the sensitivity when the horizontal component of the magnetic field is low. So this is performed by this system. The next and last circuit is the schematics of the stepper motor board. I did these schematics in order to understand the goal of that signal, Fe. Anyway, there is an up and down counting. This signal, the power supply, and the outputs, which are connected to the stepper motor. So I didn't do the complete schematic of the output stage. There is just the first stage, so this is maybe a Darlington or something like that. So there is another stage because there are two transistors for each phase of the stepper motor. Okay, but it doesn't matter. So this is the classic stepper motor control. There is nothing special except that circuit here, which is actually what I wanted to know. So you can see that this is the multiplexer. Okay, so the output here, this is the clock actually of the stepper motor. Can be connected either to that line, either to this one, depending on that signal Fe. This signal Fe permits actually to select between two inputs. So one input is a direct input, so there is a direct clock. Otherwise, the clock is divided by 256 using these two 4 bits counter. Okay, so when the signal Fe is at high level, this transistor is off, so there is a low level at that point, a high level here. This thing is inhibited, so the clock is actually the direct clock. This is the test setup for the test of this compass computer. The magnetic compass is here. This HSI is connected to one synchro transmitter. This synchro transmitter permits to simulate the gyro. And I have connected also this multimeter with the central 0 to the output of the phase detector, this signal here. This gives actually an idea of the error when that device is slaved to the compass, the value is 0. So there is also a switch which permits to select between the test mode and the normal mode. The switch is somewhere here. Okay, this is the switch. Currently the test mode is selected. First I will simulate a change of the heading of the gyro. You can hear the activation of the stepper motor for the correction, and you can see that the heading retrieves the original position. Okay, so now I will change the orientation of the compass. So you can see that the heading is always slaved to the compass. You can notice also that the frequency of the stepper motor is higher when the error is larger. Okay, so now I will select the normal mode. It is the same except that the correction is much longer. You will see that the heading follows the gyro. Actually, there is a correction, but the correction is much longer. You can hear the stepper motor. I think it will take 1 hour or so to synchronize. Okay, I will wait 5 minutes. We will see. That's all for this Compass computer. Thank you for watching and see you next time. Bye bye.